Hello, everybody. Welcome to the short paper session on systems visualization and graph visualization. We have 8 exciting presentations. If you have questions, please remember to put them on the Slido, and please remember to vote up questions you'd like answered on the Slido. So let's keep things moving. Our first speaker is Arpit Narachanya from the Georgia Institute of Technology, and this is his first in-person presentation after 4 virtual ones. Please go ahead.
Hello everyone, my name is Arpit Narachanya. Today I will talk about facilitating conversational interaction in natural language interfaces for visualization. This work was done at Georgia Tech in collaboration with Rishabh Mitra, Alex Endert, and John Stasko. There are a growing number of systems that provide a natural language interface for visualization. To develop such systems, visualization developers need to implement a user interface, a natural language query processing module, a visualization recommendation engine, and a rendering module. Developing such systems is hard for visualization developers, as they often lack the necessary skill set in natural language processing. Recent natural language-based toolkits for visualization have shown great promise to enable these developers to provide natural language interfaces in their own systems. These toolkits automate the core tasks of query processing and visualization recommendation, allowing developers to focus more on designing the user interface. For example, consider a dataset on movies and a natural language query. Show the relationship between budget and IMDb rating for action and adventure movies that grossed over 100 million. A recent natural language toolkit for data visualization, NL4DV, extracts data attributes, infers analytic tasks, and recommends relevant visualizations, all modeled into a JSON object. NL4DV and similar natural language toolkits, however, only support one of standalone queries as inputs. Because of this, end users have to specify longer queries, such as this one, to accomplish complex tasks. Also, when query processing fails, even if due to a minor error, the entire query must be paraphrased, which is tedious. So, what if the long and complex query before were to be broken into 3 simpler queries? Show the relationship between budget and IMDb rating, show only action and adventure movies, and now show movies that grossed over 100 million. We believe specifying multiple such queries in a natural sequence could enable end users to incrementally accomplish a complex task. Even systems can report specific errors and ambiguities back to the user for resolution. We call this conversational interaction. In this work, we extend the recent natural language toolkit NL4DV to support conversational interaction. We update the current architecture by including a new Conversation Manager module that helps manage multiple dialogues between the user and the system, and a new Query Resolver module that helps fix errors and resolve ambiguities in those natural language queries. Next, I will demonstrate NL4DV's conversational interaction capabilities through 2 example applications, a mind map and a chatbot. Mind maps are often used to visually organize ideas into a tree-like hierarchy. With NL4DV, users can now create and visualize multiple conversations with a dataset. For example, consider a user asking queries about a dataset on European soccer players. They ask 2 queries, show total goals by country and correlate goals and salary. They follow up on the most recent query multiple times, creating what we call conversational branches. For example, show only defenders, and how about only forwards? To process a standalone natural language query with NL4DV, developers can make a single function call, analyze query, to extract relevant attributes, tasks, and visualizations. The output JSON object consists of 2 new properties, dialog ID and a query ID, to uniquely identify this dialog and query pair. To follow up on this query, developers can pass an additional parameter, dialog, set to true. This tells NL4DV that the query is a follow-up and must be processed accordingly. To follow up on any arbitrary query that is not necessarily the most recent one, developers can also explicitly pass appropriate dialog ID and query ID as input parameters. Natural language is often ambiguous, wherein one word, one phrase, or even an entire sentence can mean different things depending on the context. For example, consider a user asking queries about a dataset on Olympic medals. They ask, show medals for hockey and skating by country. The chatbot detects an ambiguous keyword, medals, and presents a drop-down menu widget for the user to disambiguate. Similar widgets are presented for additional ambiguous keywords, skating and hockey. Once all ambiguities have been resolved, a visualization is finally recommended. Continuing with analysis, the user asks a follow-up query, group by sex. The chatbot retains the disambiguating selections from the previous queries and outputs a new stacked bar chart, now colored by sex. Internally, NL4DB stores these detected ambiguities in a dictionary, where the keys correspond to the type of ambiguity. For example, medals is an attribute-level ambiguity, whereas hockey and skating are value-level ambiguities. Both have their own separate dictionaries whose values contain the keywords potential options and the selected disambiguating choices. To resolve these ambiguities, developers make a single function call to update query with an input dictionary that contains the user's disambiguating selections. NL4DB subsequently updates the selected key in its internal data structure and continues processing. Through our initial testing, we have identified multiple areas of improvement. First, we want to automatically detect and resolve multi-turn conversational ambiguities. For example, consider a dialogue of two queries. Show only action movies, followed by what about R-rated movies? Over here, does the user want just R-rated movies or R-rated action movies? Next, we want to automatically predict compatible dialogue IDs and query IDs to follow upon from the set of previously asked queries. For example, consider two standalone queries. Show total gross across genres and correlate budget and gross. Now, if I were to ask a new follow-up query, now replace genre with content rating, can the system automatically follow up on the first query, as the second query has no genre attribute to replace? Finally, we wish to go beyond heuristics-based query processing approaches towards more learning-based approaches using transformers and large language models. However, suitable dataset benchmarks with multi-turn dialogues are currently unavailable. Existing benchmarks mostly support one-off singleton queries. To break these barriers, I call for more collaboration between the NLP and Viz communities, but wonder if the NLP community is now better equipped to make the larger contributions. One area I feel Viz can contribute is the visual unboxing of these learning-based black box models, making them more explainable, debuggable, and trustworthy for users. Just something to think about. But for now, I'm excited to share that NL4DB, along with the example applications, is available as open source software. Check it out. Thank you.
Okay, thank you so much, Arpit. While we're waiting for some questions through Slido, or we can also do it via the microphone, I have a question, which is like, this looks really cool. I'd like to try it. Can you give some more examples of what kind of conversational follow-up questions NL4DB currently supports?
Thank you. That's a good question. I can actually show it. Yeah. So the two single-line APIs that I mentioned, analyze query and update query, NL4DB's space of tasks that it supports are broken down per attribute, per task, per visualization, and add, remove, and replace. So you can add a new attribute to a visualization, you can replace an existing attribute, you can change a visualization, and so on.
Okay, great. So since we're a little short on time, please see the Discord for any additional questions. And let's thank Arpit one more time.
Thank you.
Okay, our next speaker is Nicholas Kirsten, who will just swap over.
Can you hear me? Can folks hear me? Okay. Sorry. Okay, I'll present this way, it's fine. Hi everyone, my name is Nicholas Christian, and on behalf of my collaborators John Meese and Dominic Moritz, I'm very happy to present to you our work on Vega Fusion, which provides automatic server-side scaling for interactive Vega visualizations. The Vega grammar and reference renderer have been broadly adopted by various visualization systems, such as Lyra for direct manipulation authoring, Voyager for visualization recommendation, and Altair for programmatic authoring in Python, as well as a whole host of other grammars that compile down into Vega. Despite this success, the Vega ecosystem suffers from a fairly severe scalability bottleneck because the reference Vega renderer loads the entire dataset into the browser for the initial rendering, and on many interactions must traverse the entire dataset again, all in single-threaded, interpreted, if just-in-time compiled JavaScript. A motivating problem for our research would be cross-filtering histograms for a 1 million row dataset. On modern hardware, this can take up to 10 seconds for the initial render, and drag selection interactions proceed at less than 1 frame per second. And this problem impacts the whole Vega ecosystem, which is why we were motivated to tackle it. To make this problem a little bit more visceral, let me show this simple benchmark. So I'm going to run this simple Python program, which comes from the Altair documentation. So you can see that it takes quite a while to render the visualization, up to about 10 seconds. When it does eventually render, having loaded the million rows dataset into the browser, drag selection interactions are very sluggish. It takes about 1 second to respond. So this is quite painful. Vega Fusion can be loaded with a single line of Python code. Re-executing loads almost instantly. And drag selection interactions are very smooth, up to 60 frames per second. So the key concepts behind Vega Fusion are that Vega is declarative. The JSON grammar definition and the reference implementation are not tightly coupled. Vega Fusion interposes itself between the specification and the reference renderer. It accepts any valid Vega specification, unmodified, and automatically determines which subset of the transformation pipeline contained in the specification should be executed on the server, and the rest is delegated to the reference Vega implementation. Here's a simple architecture diagram of how this proceeds. So you see on the browser, the Vega specification is accepted by the Vega Fusion planner, which partitions it into 2 specifications. The first, the client specification, contains all the elements of the Vega spec that must be executed on the client for rendering, so everything to do with interactions, scales, marks, and so on. The runtime specification contains all of the information that can be executed on, all the computation that can be executed on the server, notably aggregations, filterings, binnings, and so on, which is passed to the Vega Fusion middleware. The Vega renderer proceeds with rendering, and the client spec contains a number of data placeholders, which are filled in by the Vega Fusion middleware, both for initial rendering and anytime the user interacts with the visualization. The middleware issues queries to the Vega Fusion runtime server process, which loads the entire dataset into memory, performs the computation, and returns the response back to the middleware. You'll note that although the dataset will be quite large, it is only loaded into memory in the server process and not in the browser. So long as the queries issued by the middleware contain data reduction operations, such as aggregation, binning, filtering, that sort of thing, the response is much smaller than the original dataset. Unless, say, the Vega specification calls for a scatter plot with 1 mark per row, in which case the response will be the same size as the input dataset. The core source of performance improvement of Vega Fusion over the unmodified Vega renderer are, first of all, that the dataset doesn't always need to be transferred to the client. And secondly, the Vega Fusion runtime is written in Rust, is multi-threaded, is compiled down to native operations. Now, as you saw in my demonstration, I was running the Vega Fusion runtime on the same machine as the client, and there was already a notable performance improvement. The server process can also be run on a physically distant or different server with arbitrarily powerful hardware, at which point there's probably a network latency trade-off to be made. In addition to this architecture, the runtime contains a fine-grained caching mechanism. So the queries that are issued by the middleware to the runtime take the form of directed acyclic graphs of computations. The roots of these graphs are fixed values, such as pointers to datasets or brush extents, and the nodes of this DAG essentially map to the transformations contained within the input Vega specification. So for cross-filtered histograms, the first step is to bin the data to find the edges, and then we do 2 aggregation passes, one over the whole data set for the gray bars, and one over the data set contained within the brush for the blue bars. So for an initial render on a cold cache, we must compute all of the nodes, then we put them into the cache. And as the user brushes, the subsequent queries issued to the runtime will contain some nodes in common and some nodes will be different, in which case only the descendants of any modified nodes must be recomputed, such as G, for example, here. So this fine-grained caching allows for a number of performance improvements. For example, as a developer is iterating over a visualization, certainly the initial render state will tend to live in cache, which will speed up a developer loop. And this can also work in a multi-user scenario. So multiple users connected in totally different browser sessions to the same runtime can reuse the same cache, and essentially interactions by one user will speed up interactions by another. What I demonstrated for you earlier was the Vega Fusion Altair extension, which we developed to demonstrate that it's possible to use Vega Fusion to accelerate parts of the Vega ecosystem. Now, Vega Fusion is not limited to working only with Altair. It can work in principle with any piece of the ecosystem because we targeted sort of the lowest layer in that stack. And of course, it's not limited just to cross-filtered histograms. Vega Fusion plus Altair, for example, will work with any unmodified Altair program, so you can develop a visualization on a small data set. You don't need to sort of split it up again into a client and server piece, and it will accelerate any operations such as aggregation, binning, or filtering. Some sort of numerically benchmarked results here. The initial render is about approximately 15 times faster, and drag selection interactions display frame rates that are between 15 and 100 times faster, depending on sort of the extent of the brush. In terms of future work, we're working on greater coverage of the Vega transformations in the runtime. For example, regression is not supported at the moment. We're working on a more sophisticated planner that can, instead of just moving everything it can to the server, take into account data set size and network latency. And finally, instead of always copying the data into the runtime memory, query upstream SQL databases or clusters, essentially moving computation to the data rather than vice versa. Thank you very much for listening. I'd be happy to take any questions, and please note that Vega Fusion is open source software available at github.com/VegaFusion.
Okay, great. So we have a question from Slido. Anna Christen asks, does Vega Fusion have the same data size limitations as Altair?
No. So Vega Fusion, in fact, doesn't have any hard-coded data set size limitations. For example, in the example I showed, I had to turn on the Altair data server to get the unmodified Altair to work, but Vega Fusion will happily scale up to the size of available RAM on the runtime.
One more question. Does the performance gain depend on there being data aggregation in the spec?
Yes, that's right. So if there is no data aggregation or filtering in the spec, the Vega Fusion planner will essentially just pass those operations straight to the reference implementation. So Vega Fusion in principle will never be any slower than a reference Vega renderer. It will only move operations to the server that are supported by the runtime, such as aggregation, filtering, sampling, and a couple others.
All right. Thank you so much. Let's thank Nicholas again and switch speakers. So please see Discord for additional questions. Our next speaker is Hana Bako, and she is a PhD student at the University of Maryland, currently interested in internships and collaborations.
All right, great. Can we hear me? All right, so hello, I'm Hannah, and today I'll be presenting our work on streamlining visualization authoring in D-Tree through user-driven templates. And this work was done in collaboration with all these beautiful women who at the time were undergrad students at the University of Maryland, and of course with my advisor, Leilani Battle. So, D-Tree is one of the most prominent libraries for creating web-based visualizations. And this is in part due to the expressiveness of D-Tree and also its ability to support a variety of interactions and animations when integrated directly into web pages. But the problem is D-tree is difficult to use. So first of all, D-tree has a steep learning curve that creates a barrier of entry for new users. So in addition to learning D-tree, a user must have knowledge of HTML, JavaScript, and CSS, and also possibly scripting languages like Python. And also, D-tree requires a lot of effort to create even the most basic of data visualizations. And the complexities of D-tree is often a deterrent for users from effectively using it. And even though simpler tools like VegaLite, Data Illustrator, and Lyra exist, for users who have to use D-tree, they can't easily pivot to these tools. So how can we simplify the authoring process for such users? Well, templates help us. Templates provide a concise way of simplifying D-tree authoring, and the appeal is that templates provide reusable components that users can use to quickly generate and iterate over their visualization designs. And templates have also been successfully used in visualization tools like raw graphs, IV, as well as in the construction of reusable style templates done by Harper and Arguala. However, these templates do not often capture the strategies that reflect how D-tree users actually use libraries and code to create visualizations. So the main question we aimed to answer was to understand how can we create reusable visualization design templates that match how D-tree users actually use D-tree. And we had two core objectives that we wanted to achieve. First, to understand the visual and interactive patterns that D-tree users frequently use when programming visualizations, and also to identify intuitive implementation strategies that are commonly used by these users. And our approach to this was to first gain an understanding of how D-tree users currently use D-tree in the wild. And this we did in 4 steps. First, we identified and scraped a corpus of D-tree visualizations that were shared online. The second step was to code these examples based on the visualization and interaction patterns present in each example, and then analyze the coded examples. And finally, we synthesized reusable templates from all these examples. So in total, we coded 2,500 examples from blocks.org, Observable, and GitHub. However, we had quality issues with the examples from Observable and GitHub, so we focused our analysis on the blocks corpus. And within our blocks corpus, about 79% of all the visualizations that we found were standard visualizations. And we classified standard visualizations as the 21 D-tree visualization types that were identified by Battle et al. In their Beagle paper. And what we find is that the top 5 most popular chart types, which are basically bar charts, geomaps, line charts, scatter plots, and force-directed graphs, represent roughly 80% of all the standard visualizations that were created and shared by users. And we find that this trend remains consistent across the Observable and GitHub repositories, save for slight changes in the actual visualizations in the top 5. And what this indicates is that we can really just support most D-tree users by focusing on the most popular visualization types that people create and share. And we also coded the interactions that were implemented in each visualization. And we find 3 interesting observations. So first, some interaction widgets appear to be universal. And this was very prominent with widgets such as hover, which were pervasive across all visualization types. We also see that the number of interaction widgets used vary across visualization types. So for certain visualizations, including at least one interaction was the convention. For instance, about 49% of the line chart examples had absolutely no interactions implemented, while 82% of the graphs that we looked at had at least one interaction implemented. And this leads us to our third observation, where we see that certain interaction widgets were tightly coupled with specific visualization types. So for instance, graph charts tend to always be implemented with a drag interaction, while geomaps were more likely to have a zoom interaction implemented compared to all the other visualization types. So the next step in our analysis was to synthesize reusable templates for the most popular visualization types in our dataset. And D-tree's API really just made this easy for us because the syntactic structure for creating visualizations remains the same. So for instance, here we have 3 implementations of scatter plots that we found in our dataset. And while these are 3 different implementations, we can see that the underlying code for creating and binding data to the point marks basically remains the same, save for some very slight stylistic differences. Similarly, we found a prevalence of code reference in the community. So several code blocks contain direct links to other repositories or examples as inspiration or sources of code for their design. So in this example of code, we can see that this user is referencing a GitHub repository. And when we examine the code from that GitHub repo, we can basically identify whole chunks of code that were directly replicated in this participant's example. So using these observations, we manually extracted common code sections from multiple examples in our corpus for each of the visualization types that we saw. And we combined these common code sections into working generic implementations for templates which a user can change and fit to their data. But what exactly do our findings mean for visualization authoring? Well, our findings highlight striking structural similarities in implementation code for various visualization types. However, recent literature has found that users often struggle to reuse existing D3 examples because they're just simply not modularized, they don't know what to use. So to support users, we need to provide modularized templates that they can piece together when creating their visualizations. We also see a high fraction of D3 examples that rely on interactions to explore underlying data. However, there's like multiple combinations of interactions and implementation conventions that a user can choose from. So to save time and effort for users, we can automatically recommend a list of appropriate interactions that they can implement for each visualization type. And finally, the large and active D3 community provides a unique opportunity for us to co-design effective visualization tools. So to summarize, we find that a small subset of visualizations make up the most commonly used charts. Certain interactions are conventional for specific visualization types, and there's a need to provide guidance for users on what interactions they can use. And visualization templates can be used to simplify programming, and we also contribute a collection of user-driven templates that encapsulate the practices of on our OSF repository. Thank you.
Okay, so we have time for one question. So are the templates parameterizable and combinable to change how chart types are generated? And if so, do those parameters go beyond the stylistic modifications to creating compound charts, for example, like an embedded pie chart in maps?
Not right now. This work was primarily to support just the very basic chart types that people create. But we are currently working on extending this to explore research in that direction.
All right, thank you. You have several more questions to answer on Discord, but let's thank Hannah again. Okay, next up we have Jonas and Jeroen Vanderdonk, who are twin PhD students doing applied research. So let's welcome them as they get set up.
Okay, so hello everybody. My name is Jonas van der Donkt, and together with my twin brother, Jeroen, I will explain how we aim to improve effective visual analytics for large time series. So first, we will focus on the title. With the term effective, we want to emphasize effectiveness with regard to end users. And for large time series being a rather complex modality to deal with, we envision data scientists as end users. So we can take a data scientist perspective. And for these data scientists, there are several facts. Mainly, Python dominates currently the data science ecosystem. So having a tool which integrates into Python environments is really important. Next to this, web-based environments such as Jupyter Notebooks are most popular among these data scientists. Thirdly, interactive visualizations enable such effective exploration. Being able to zoom in on regions of interest is really important. And finally, as we will deal with large time series, scalability is important. Now, the other part of the title, time series. The most intuitive way to first analyze a time series is visualizing it over time via line chart. With this, you can already get a gist about the range of the data, whether there is a trend, some seasonality, and so on. However, when we deal with large time series, this is not feasible anymore. Visualizations tend to become slow and unresponsive. And this is caused by a single fact. All data points are shown in the front end. Here you can see a screenshot of a Jupyter notebook in which I aim to visualize all my data. And the browser says that this notebook is slowing down my whole browser and whether I want to stop it. To this end, we developed Plotly Resampler, which aims to not visualize all data points in the front end, but downsample or aggregate the data respective to the front end view and only showing these aggregated data points. In this demo, over 110 million data points are visualized. How is this achieved? When a user zooms in on a region of interest, a callback will be triggered, which will be sent to a backend, which then performs a data aggregation method and will then send the aggregated data for that region of interest back to the front end. Plotly Resampler is fully open source, has an MIT license, and has already more than 70,000 downloads. It is also well documented. So when we look now back at those requirements for effective visual analytics and put these in a table and map this to the most popular visualization packages, we see a common trend. No tool is both interactive and scalable. For example, Matplotlib is a non-interactive visualization library and is only somewhat scalable, whereas both Bokeh and Plotly are interactive tools, as these are JavaScript-based, but lack the scalability component. So by wrapping the Plotly library with Plotly Resampler, we create an interactive, scalable visualization tool. So to make it more concrete, the Plotly Resampler functionality will separate the visualization into two components. A Plotly JavaScript frontend, which contains the aggregated view of the lower dimensional representation of your time series, and a Dash backend, which contains all the raw data. And through optimized callbacks triggered by user graph interaction events is this interactivity ensured. Plotly Resampler integrates seamlessly in Visual Studio Code, in Jupyter Notebooks, in PyCharm, and in Google Colab. So when we look back at this table and extend Plotly with Plotly Resampler functionality, we can see that all the requirements for effective visual analytics for large time series for data scientists are met. Now, Jeroen will take the floor and will try to show a demo.
Okay. So now that my brother has introduced Plotly Resampler, I'll try and showcase the need and usability. I'll have two notebooks open. Here on the left, we'll try to visualize 10 million data points using plain Plotly. I'll start running it. Oh, yeah, I first need to uncomment it. So, as you can see, it takes quite some time to render those 10 million data points. In sake of time, I'll go over to the next notebook, the notebook on the right, where we will be doing exactly the same, but now we'll be using Plotly Resampler. Again, I'll uncomment the code. And as you can see, it gets rendered rather immediately. We can zoom in and interact with the visualization, which seems to be quite useful as the added value of interaction already uncovers the underlying noisy sign. Okay, now that we've showcased Plotly Resampler on some dummy data, we'll also show a more advanced visualization on some real-world data. Here, I will load some sleep data consisting of EEG, EMG, and EOG signals. In total, we are talking about 382 megabytes or 24 million data points. So I'll load this in this visualization, which starts on this port. And as we can see, we get directly a full overview of the visualization. We can actually see that now Plotly Resampler complies with Scheindermann's mantra, overview first. In this overview, we see that around 24 hours of data has been collected and that in this hypnogram, the patient was asleep for roughly 6 hours. So let's zoom in and filter. When we zoom in, we notice actually, oh, by the way, my browser on the left just crashed trying to visualize 10 million data points using Plotly. So when we zoom in the sleep example, we see that lower EMG activity corresponds to deeper sleep stages. Also, higher EOG or eye activity maps onto the REM sleep stage. So let's now zoom in and get some details on demand. When we zoom in here, we see that the rise in the eye activity, together with the brainwave activity and basal activity, corresponds to a transition from the deep REM sleep to a lighter wake sleep. Even this spindle indicates actually that for the physician, the patient went from N1, the first sleep stage, to the wake sleep stage. So this concludes our demo. Let's get back to the slides. There are still some other aspects we haven't covered yet. For example, the scalability of our toolkit, which, spoiler alert, scales better than existing toolkits, the research value, and the architecture. All these things you can find back in the code, the documentation, or the paper. Finally, we show an annotation app using Plotly Resampler. In this annotation app, we annotate some data, and we can save it, and this is realized by building upon the Plotly ecosystem. As already said, Plotly is an open source library, so the GitHub link is here above. We thank you for your attention and are happy to answer any questions. Okay.
So thank you for your great talk. We have several questions on Slido. The first is, what is the advantage of the Plotly resampler approach over rendering with WebGL?
I think rendering with WebGL is a rendering approach, whereas we have a data aggregation approach. So all the data or the functionality of sending the data to the front end is still available, if I'm correct.
Yeah, also, I think Plotly also incorporates some GL components. For example, in the demo, we showed that we used scattered GL traces to add lines. This is already in GL-enabled speedup. So actually rendering via WebGL isn't sufficient for large amounts of data. Additionally, when you're working on a remote environment, you want to visualize and send, for example, tens of millions of data points over to a front end, a JavaScript front end, that is not feasible. So actually there is a need for data aggregation for scalable visualizations.
All right, and one more before sending these to Discord. How specific is the downsampling approach to the details of Plotly? Could this approach be applied to other performance-constrained libraries like Matplotlib and Altair?
Yeah, exactly. So the downsampling approach is basically a very optimized downsampling algorithm, which is completely not tied to Plotly. And we are also thinking to decouple this in our library and make this available as a separate Python library with wrappers that can be used then for example, bokeh or other interactive visualization packages.
All right, thank you. Okay, our next speaker is Sungmin Lee, a computer science PhD student at Georgia Tech.
Can you hear me? Oh, great. All right, good afternoon, everyone. I'm Sungmin Lee from Georgia Tech, and I'm happy to present our work explaining website reliability by visualizing hyperlink connectivity. I'm presenting on behalf of my co-authors, Sadia, Hegyu, Jay, Omar, Vibor, Ankit, and Polo. So web misinformation has had far-ranging repercussions. For example, web rumors on COVID-19 have turned people not to get vaccinated, while Pizzagate conspiracy theory, which was political web rumors in 2016, had resulted in gunshots and death threats to innocent people. Therefore, there have been a lot of works to alert people to web misinformation. However, the existing works actually did not provide any explanation about how each of the websites engages in spreading false information. To fill this research gap, we present misfits to help people assess website reliability by providing those kind of explanations. So the rest of the presentation will be as follows. First, I'd like to introduce how we designed misfits and then share the result of user study and design lessons that we have learned. So I'll begin with the design of misfits. For the website reliability, misfits is based on the recent findings that a website's reliability is closely related to how it is connected with other websites via hyperlinks and how it is shared on social media. So for the data set about website reliability or social media mentions, we combined and filtered the existing data sets and did web scraping and used the Twitter API and could obtain the data for 2,000 popular websites. So to design misfits, we established 3 different design goals. First, we aim to design a graph visualization which is very easy to understand for the general public who has no background in visualization. Also, we try to make misfits more credible and easy to use. So now let me explain misfits more in detail. When a user visits a website, misfits is displayed interstitially, which means that misfits is displayed over the blurred website and users' interactions are all blocked to enhance the usability. Misfits consist of 2 windows, main window and Twitter window, and I'll begin with the main window, which visualizes hyperlink connectivity. So in the main window, each of the website is represented as a circle whose color indicates its reliability labels. The website being visited is shown in the center, while the connected websites are arranged along 2 concentric rings. Here, the directly connected one-hop neighbors are on the inner ring, while 2-hop neighbors are on the outer ring. And the hyperlinks between 2 websites are represented as edges, and when a user hovers over a node, the potential information flow of the hovered nodes are shown as the animation. And by clicking a button in the tool, the users can see the summary of the distribution of the connected website's reliability labels like this. So next, I'd like to introduce the Twitter window, which summarizes how the website is shared on social media. Since some of the prolific spreaders of false information share multiple different controversial websites, we first showed the percentage of the controversial websites that are shared by the Twitter users who mentioned the visited website. And at the bottom, we show the number of the bot accounts sharing the visited website, since bots are commonly deployed to spread false information on the web. And next, I'd like to share the result of user study. To validate the effectiveness of misfits, we conducted a large-scale user study with 139 participants. We first asked them to visit 2 websites, each of which are 1 controversial and 1 verified website, and then use misfits to determine whether the visited website is a reliable information source or not. And then we asked them to rate their experience with misfits as a score from 1 to 5. And this is the summary for our user study, and you can get more detail from our paper. And I would like to introduce some key takeaways of this user study. First, we could see that misfits was indeed easy to use and understand, and also very helpful to assess website reliability and connectivity. Also, the node-link diagrams for hyperlink connectivity was actually very easy to understand for general public who are not expertise in visualization. And we believe this result is particularly meaningful since there have been very limited research on the graph visualization for general public who has no experience in visualization. And this result can suggest our visualization community to investigate more about this topic in the future. Also, the hyperlink connectivity appeared to be very helpful to assess website reliability, and the interstitial visualization was also helpful for misfits usability. And lastly, I'd like to share some design lessons that we have learned throughout our iterative design process in discussion with cybersecurity experts. So first of all, we could learn that we should carefully address the label wordings for website reliability labels. So at first, we named each of the labels as misinformation, reliable, and unlabeled, but soon realized that the term misinformation actually does not cover all types of false information on the web. Moreover, some users might feel very offended if the websites they have commonly visited are labeled as misinformation. Therefore, we changed the label names to controversial and verified, which are more neutral. Also, we learned that revealing sources for website reliability labels is very important for the credibility of Misfits. The earlier design of Misfits did not contain any statement about where the labels came from, and some of the participants of our public study were very concerned about the potential biases in the labels. Therefore, we added the statement about where the labels came from, and far fewer participants of our user study were concerned about the credibility. So returning to our design goals, now we could see that Misfits was indeed understandable, credible, and easy to use tool. So in this presentation, we introduced Misfits to help people assess website reliability by visualizing hyperlink connectivity and how it is shared on social media. This is the end of my presentation, and thank you for listening.
Thank you, Sung-min. So you have several questions. The first is, wonder if Elon Musk would be interested in your work to assess Twitter content, says Vidya Settler. And on a more serious note, is hyperlink connectivity a good proxy for website reliability, or if there are additional heuristics needed for fake or malicious content?
Actually, that's a very good question. So the point that we used the hyperlink connectivity for the reliability was based on the recent paper or literature, but I think it might be kind of heuristics, so I think we should address that point more seriously and leave it as our future research direction.
All right, and Anonymous is curious, how do you determine if a website shows misinformation?
Actually, that's another very good question because, misinformation is somewhat very subjective and might depend on how a person defines misinformation. That is the reason why we use the existing data sets to be as objective as possible. But if that is kind of controversial to label, we left them as unlabeled. And also that was the reason why we used the term controversial, because many people might have very different opinions about the website reliability. Yeah, but actually, I think that is a very good point, so we should be really careful about that.
All right, so we don't have quite time to squeeze another one in, so let's thank Sung-min again. And please see Discord for the other questions. All right. Our next speaker, Alex, is an assistant professor at American University and looking to hire a postdoc in the area of this presentation.
Hello? There we go. My name is Alex Godwin, and I'm very pleased to share this work with you on finding a technique for visualizing paths through spatial networks. So spatial networks, network with a geospatial component, so some sort of longitude and latitude labeling the edges and the nodes themselves. These are tricky and interesting. There are two measures for physical distance. There are the network hops, then there's also physical distance. So how long does it take to get from one node to another? Now, network distance, as we know, can be meaningful. We're looking for things like central nodes, clusters, and clicks in the network. But spatial distance can also be meaningful. Tobler's law tells us that near things are more related than distant things. So when things are close together, we might ask different questions about them. To give you an example, it's only about 18 miles or 30 kilometers from the northern New Mexico city of Español to Los Alamos. So it'd seem reasonable that the energy grid between these two places would be fairly closely connected. However, if we look at a force-directed diagram, the network distance is actually about 9 to 10 hops from them. So you'd actually need a trip out to the distant city of Shiprock at about 195 miles or 314 kilometers from both endpoints. So this distance in terms of network hops actually relates to something fairly far in terms of physical distance. Consequently, the Shiprock node also has a much higher betweenness centrality in the local network because it acts like a central path between distant endpoints like Español and Los Alamos. So a lot of things route through it. Now, there's a lot of related work to what I'll be talking about today. Schottler et al. In their survey identified no fewer than 95 techniques for visualizing and exploring the design space of geospatial networks, classifying them within a design space along 4 dimensions. They highlight the tension and trade-offs between maintaining geospatial fidelity while also emphasizing network structure. This also relates to the work of Javed and Elmquist, pointing out the benefits for loosely coupling representations in juxtaposed views for network visualizations. We see systems like matrix that compose small multiples into a view where visual links are connected through a secondary adjacency matrix, and systems like transmogrifiers, where we're actually using distortion to create an axis alignment for a curved path through space that's then linearized. Other work like hot sketch and attribute signatures treat the path through space as a form of querying, in this case, point-based or census-based data, to look at how that data actually changes from the beginning of the path through to the end. So the through line here is that there are 2 big connections to previous work. So how do we connect space and network through multiple juxtaposed views? And also, how do we treat the query of a path through space, which will allow us to query a spatial network instead of point-based data, and use that path to actually create a distorted layout and populate a juxtaposed view. So our secondary view is going to be a force-directed diagram, which is good. It's very familiar. So they can usually be interpreted by non-experts, and they're typically quite good at revealing topological structure, such as network distance, betweenness, and centrality. There are some common problems across all force-directed layouts. There's, of course, the hairball problem. But for spatial networks in particular, there are some specific issues. They're non-deterministic. So between iterations or between refreshes of the diagram, the layout could be completely different with nodes in a brand new position. The layout is also not informed by geography in any way. A node that's at the top of the force-directed view might actually be close to the bottom or the southern region of the map. So we're going to need to modify the force-directed layout in a few ways. So how do we actually create a force-directed diagram from a map? I propose the following. We're going to create additional forces that work within the existing adjacency forces and set the magnitude and direction of these forces from spatial arrangement of nodes on a map. So I propose we use a path as a query of spatial arrangement. So whatever our query region is, we can create a path through it, creating an arrangement of axes, so from left to right and from bottom to top. So if we're looking at the energy grid around Washington, D.C., the path allows us to answer some questions about the relative distance and arrangement of the points on the map and that path. So what is the closest line segment along this path to any given point? That gives us a space for vertical positioning. What is the ordinal location from the beginning of the path at the bottom to the top of the path at the end? And depending on whether it's on the left or the right-hand side, in this case I've used blue and red to sort of help you understand the way that these forces are going to be represented, though that's not necessarily a final coloring. Allows us to determine a horizontal axis as well, based upon the overall distance from the central medial line in the middle. So the typical forces in a force-directed layout, a charge force that pushes nodes apart from each other, a link force that ensures that nodes are connected to each other and pulled together, a collision force that pushes nodes away to avoid overplotting. Adding to these, we're going to be incorporating spatial forces. A y-axis force that pushes the node toward a scaled vertical position as a function of its distance from the start of the path, an x-axis force that pushes the node towards a scaled horizontal position from the midpoint of the network layout. And the magnitude of that force is going to be the node's distance from the path, the direction determined by port, so to the left of the line, or starboard, to the right, depending on whether or not you do a lot of sailing. This is implemented within a D3JS force simulation using some of its existing structures. We're also using TurfJS for spatial queries and Mapbox.GL.js for displaying the map. This allows us to create a force-directed layout that retains many of the qualities of the map-based layout. And it's also more deterministic than what we would have created from a strictly force-directed layout. Adding to that, this technique is applicable to points, lines, and more complex curved lines, such as this traveling salesman path throughout the continental United States. We're using an aggregation from applying the dbScan clustering to also create a frequency view in the center so that we can brush and filter across the path. So I'm going to switch over to, let's see here. Very quick. So here we have a path moving from DC to LAX, and a portion of the path is selected in the middle. We can see a frequency view for the nodes as they move into view on the right-hand side. Zooming into our area on the map that I was talking about before, so New Mexico. If I look at a smaller portion of the map, then move away from it and return, we have a fairly deterministic layout for a spatial arrangement. So again, time is up. Thank you for your time. We're going to be looking at trying to apply this to much larger scale networks. So things that actually move across the entire worldwide network of global seafood trade and social connections. So I am looking for a postdoctoral person to come and work with me on this over 2 years. Thank you for your time.
Okay, thank you, Alex. So we have time for one question. So you mentioned this is a start. So what do you think are the next big features on the horizon in solving this problem?
So I think certainly taking a look at non-local networks. So this works fairly well whenever you're joining things like infrastructure networks where the edges are fairly close together. So transportation, energy networks, things like that. As you begin to look at transportation networks across air or across large positions of the ocean, you have to incorporate additional interactive features for looking at the number of hops away from each of the included nodes. So I think that's definitely the next step, is trying to figure out how to incorporate much larger scale networks.
Okay. Thank you, and please see Discord for additional questions.
Thank you.
Oh, we almost made it through without that happening. All right, so our next speaker is joining us from the virtual conference. So let's all welcome Anita Mahinpe.
Hello everyone, I'm Anita Mahimpe, and today I'll be presenting our paper titled LineCap, Line Charts for Data Visualization Captioning Models. Scientific articles use data visualizations to enhance reader comprehension and convey additional information. Figures are usually accompanied with captions that can help readers understand the purpose of the data visualization. These figure captions are often the only means for visually impaired individuals to access the content of the visualization. But figure captions don't always follow accessibility guidelines. This motivates the development of systems for automated figure captioning. A very closely related field is automated image captioning. This field has seen some major advances using deep learning models trained on large datasets of image and caption pairs. Can similar deep learning models be applied to figure captioning? To answer this question, we need labeled datasets of figure and caption pairs for model training. But what information should these captions include? Past research has shown that figure caption information generally falls into 4 categories. Level 1 and 2 captions convey low-level details like the chart type, axes labels, and minimum and maximum values. This information is perception independent. Level 3 and 4 captions contain high-level details like trends and patterns or contextual information that requires domain knowledge. This information is perception dependent. Previous chart parsing and captioning datasets and models have successfully extracted low-level information from figures. But what about level 3 details? Can this success extrapolate to more complex, perception-dependent captions that describe the chart trends and patterns? We investigated this in the case of scientific line charts. We crowdsourced level 3 captions on Amazon Mechanical Turk using a question template to guide web workers in describing the trends for all the lines in a chart. Annotators were first asked to count the number of lines in the figure. Then they were asked to individually describe the trends of each of the lines. Finally, they were instructed to summarize the trends of the overall chart. An initial batch of data showed that many web workers do not know how to correctly describe certain line trends. In some instances, web workers only provided simple, low-level details such as the start and end point of the lines. Because of this, we decided to provide annotators with a list of common terminology for describing line trends. While this limits language variations in the collected captions, it significantly improves the accuracy of the description, which is of greater value. Using this setup, we collected descriptions for over 3,000 line charts, with the average line description being 14 words long. In addition to describing the individual line trends, annotators tended to state the relative position of the lines in the graph and mention line intersections. After post-processing the collected captions, we set up a deep learning model to establish benchmark performances on our dataset. We opted for a two-stage system that first predicts the number of lines in the chart and then generates a description for each of the lines. The model was implemented using the CNN-LSTM architecture introduced in previous research for the task of figure question answering. After training the model for 100 iterations, we reached an accuracy of 94% for predicting the number of lines in the chart. The accuracy was greater than 90% for both single and multi-line charts. When generating captions, however, the model was successful at predicting simple trends for single-line charts, but it struggled with complex trends in multi-line charts. To quantitatively evaluate the generated captions, we used 3 automated evaluation metrics that are commonly used for evaluating image captioning models. We also set up a survey on Mechanical Turk and asked annotators to rate the accuracy of 100 generated figure descriptions on a scale of 1 to 5. Based on human accuracy ratings, the descriptions for single-line charts are the best. But the automated evaluation metrics have higher scores for the multi-line charts. We calculated correlation scores between the automated metrics and accuracy and observed very low correlations between blue and cider scores and human accuracy. Furthermore, we only saw weak to moderate correlation between blurred and human accuracy. Through this case study, we've identified 3 main insights toward developing deep learning models for automated data visualization captioning. First, we've established that it is feasible to crowdsource high-level descriptions for data visualization captioning. However, due to the more complex and technical nature of high-level figure captions as opposed to image captions and low-level figure captions, web workers need additional guidance and training to generate accurate captions. This could come at the cost of reduced language variations, but ensures better caption quality. Second, there is a need to establish appropriate methodology for automated evaluation of generated figure captions. Previous research has shown that many automated evaluation metrics aren't very good at assessing the quality of image captions. Evaluating figure captions has additional nuances that amplify this problem. For instance, unlike image captions, changing the order of phrases in a figure caption is more likely to completely change the meaning and thereby the accuracy of the figure description. Yet automated evaluation metrics do not heavily penalize such inaccuracies. Finally, models could benefit from adding intermediate training tasks such as data extraction and line tracing to resolve the challenges of captioning multi-line charts. To summarize, in this work, we have created a dataset for automated figure captioning of line charts, have established baseline performances on this dataset, and have identified 3 main insights for future research in this field. Thank you for listening to this presentation.
Hi, Anita. We're so glad to have you here with us. I don't know if you can see this, but the room is quite packed. There is one question we have on Slido. Is there a reason why the accuracy started high with the first and 2 line charts and then takes a dip at 3, but then goes up again at 4 and 5?
So I think part of the reason for that is that we have a lot more diverse set of line charts with 1 to 3 lines. So there's probably more diversity in the category of 3-line charts, which is contributing to that, because something that we noticed, for instance, with multi-line charts is that at times there can be lines that are overlapping, and that's something that causes the model to have difficulties in identifying how many lines there are in multi-line charts.
Okay, thank you so much. We don't have time for another question, but please check out Discord, and thank you again. Okay, our next speaker is Jiwon Choi, who is an undergraduate from Sungkyunkwan University in Korea.
Hello everyone. I'm Jiwon Choi from Interactive Data Computing Lab of Sungkyunkwan University. Today I'm going to present Intentable, a mixed initiative system for intent-based chart captioning. Visualizations often accompany captions. These captions offer numerous benefits to both authors and readers, such as explaining a visual mapping, emphasizing the author's takeaways, and providing better accessibilities for visually impaired readers. However, authoring captions remains a time-consuming and demanding process is because authors should analyze data and compose the content manually. Many systems have been proposed to address the drawbacks of authoring captions for visualizations. Storytelling systems help the author to link the textual annotations with visualization elements. Template-based and machine learning-based chart caption generation systems automatically generate textual captions using fixed template or machine learning models. However, these systems have some limitations. First, storytelling systems do not generate captions themselves. Instead, authors should write captions manually. Template-based generation systems offer limited scalability and diversity because they are based on a relatively small number of hand-engineered templates. Machine learning-based generation systems are hard to find control because these systems automatically generate captions when chart images or table data are fed into end-to-end models. Intentable overcomes these limitations by taking a mixed initiative approach. In addition to chart specification and table data, Intentable allows the authors to express their takeaways through an interactive interface. Intentable composes a sequence called caption recipe and synthesizes natural language captions using a transformer-based machine learning model. Let's see the interface of Intentable. The author first chooses the action type of intent. Then, the author selects the target visual mark to describe. Intentable automatically generates the caption based on the author's input intent. We first collected 105,000 instances from the web. Each instance consists of table of data, chart spec, and caption. However, these captions are merely plain text without annotations, so we cannot build models to consider the author's takeaway using these captions. To make models to consider author's takeaway, we have to extract takeaways from instances. To extract takeaways from instances, we first define caption intent that represent the author's takeaways. Caption intent is the action and target pair. Action is a type of semantic content, and target is keys and values of visual marks that the caption contains. Next, we conducted a rule-based automatic tagging process to identify caption intents from plain captions. Inspired by the 4-level model, we define intentables for action types. In the 4-level model, the semantic contents of captions were classified into 4 levels. As you see, intentables for action types correspond to 4-level model. However, contextual and domain-specific sentences are removed from captions because these sentences cannot be inferred from data tables and charts. We label 4 action types for each sentence. Then we identify target objects from caption sentences. In the example, you can see 2 sentences contains 1 target each. After the tagging process, we compose full caption recipes as a source sequence for the training step. This is an example of a caption recipe in our test set. At the head of the caption recipe, there are metadata of the chart and tables such as chart type, title, and unit. Next field is list of caption intents. We have 2 intents, trend and describe here. Target field of trend intent has 2 target objects about the start and end of the period. To generate numerically correct sentences, we embed extra fields in caption intents such as diff and feature. These extra fields help models to be aware of relations between targets without accessing the full data table. Based on the caption recipe of previous slides, our model generated these captions. You can see that caption reflects the various facts and user intent included in the recipe. In the training process, we performed data augmentation for better controllability. We randomly removed the subsets of intent sentence pair from recipe. As a result, we used almost 203,000 recipe caption pairs for training. Then we fine-tuned multiple transformer-based pre-trained language models to generate intent-based captions. In the quantitative evaluation, we compare performance between 2 different tests, table test and intent test. Table test is similar to fully automatic generation task in a previous study. We compare 2 different tasks because there are no baseline systems that generate captions considering intent. The evaluation results show model produced more accurate caption when intents were given than when complete data tables were given. This implies that intent-based generations not only supports user intervention, but also produces more accurate caption. We found some qualitative findings of our models. Our model learns the relationships between orders of magnitude such as million, billion, and trillion, and performs conversion between the units. In the example, the target value was given in billions, but the model converted it to trillions and round off the value. We provided extra field diff to recipe for numerical reasoning without accessing complete data table. To see the impact of this extra field, we trained model without this field and checked whether the model choose a correct verb such as increase or decrease. Without diff field, the F1 score of classification was 0.76, while with diff, it increased to 0.88. This experiment indicates that the model exploits the diff information in generating captions. In conclusion, we build machine learning models that generate captions based on the author's intents. Our system can produce more accurate captions than previous fully automatic generation systems. Thank you for listening.
Okay, thank you. We've got a question from the Slido. So they wonder, is the training data set accessible to the public?
Yes, we scraped data set from statista.com. We scraped data set from publicly accessible websites. So we can easily scrape the data set with our scraping scripts.
Okay, and is this available at the GitHub link?
Oh yes, no, not the full data set, but the scraping script is in the GitHub.
Okay, and also, so you're thinking of expanding to additional chart types. What other intents do you think might arise when you expand your set of charts?
Excuse me.
All right, if you expand the set of charts that you support, do you think there will be additional intents? And if so, which?
I can add additional intents like patterns of our chart like that. We can extend to that types of intent.
Thank you so much. Please look at Discord to continue the conversation. So let's thank Jiwon again. So we're at the end of our session. So thank you so much to the tech chair and the student volunteers here. You guys for being such a great audience. And let's thank all our speakers again as well.